Before introducing quantum mechanical expectation values, I would like to give you a very useful review of the ordinary mathematical meaning of an expectation value. The example here considers tossing two coins 16 times. Let the random variable x be the number of heads obtained in a given toss of the two coins. Since we are tossing two coins, the possible values of x are 0, 1, and 2. Now suppose the outcomes of the experiment are as follows. So we have 0 head occurs 4 times, 1 head occurs 7 times, and 2 heads occurs 5 times. Then the average number of heads per toss is calculated by weighting each value of x by the number of times it occurs, and then dividing by the total number of trials. So we get the expression shown here. The result is 1.06. So each term in the numerator is the number of heads obtained per toss times the number of times that outcome occurs. That is the average value of the random variable x in this experiment. We then rewrite the same calculation in a slightly different but more instructive form as shown here, which is exactly the same as the one shown above. Here, these fractions are the relative frequencies for the different values of x in our experiment. In probability language, they play the role of probabilities estimated from repeated trials. This is exactly the idea of an expectation value. We multiply each possible outcome by the probability or relative frequency of that outcome, and then sum over all possibilities. So the ordinary mathematical expectation of a variable is really a weighted average. Why is this review important here? Because in quantum mechanics, expectation values are also weighted averages, but the weights are determined by the wave function. In particular, probabilities will be related to the absolute square of the wave function, and observable quantities will be associated with operators. So this coin toss example is serving as a bridge. It reminds us of a familiar statistical idea before we move to the quantum version, where the mathematics becomes more sophisticated, but the conceptual core remains the same. An expectation value is not just a single raw measurement. It is an average over many possible outcomes weighted by their probabilities. Before we go deeper into expectation values in quantum mechanics, let's consider a thought experiment, which is measuring a particle's position. This is a very important thought experiment that motivates the meaning of a quantum mechanical expectation value. So imagine a particle in a state described by a wave function whose probability density is the absolute square of psi, as shown in this figure. The probability distribution is spread over a region of space. Suppose we perform a position measurement and find the particle at point C. Then what would happen if we immediately performed a second measurement? The key idea is that the first measurement collapses the wave function at point C. That means once the particle has been found at point C, the state is no longer described by the original spread out wave function in the same way. Instead, the act of measurement changes the state. Therefore, any position measurement made immediately after the first one will simply repeat the same result, which is the particle will again be found at point C. So this thought experiment is extremely important because it warns us against a common misunderstanding. Suppose someone tried to define the position expectation value by repeatedly measuring the position of the same particle in the same state, one measurement after another, and then averaging the result. That would not work. After the first measurement, the state has already been altered by the measurement process. So repeated immediate measurements on the same system do not sample the original probability distribution. They simply reproduce the post-measurement result. This is why in quantum mechanics, expectation values must be interpreted as the so-called ensemble averages, not repeated measurements on a single system without re-preparation. In other words, if we want to determine the expectation value of position for a state psi, we should imagine preparing a large number of identical systems, each in the same initial state psi, measuring the position of the particle once on each system, and then averaging the results over the entire ensemble. This is the proper quantum mechanical meaning of an expectation value. The probability density, the modulus squared of psi, tells us the statistical distribution of outcomes across many identically prepared systems, not the result of repeated position measurements on one undisturbed particle. So quantum measurements are not passive observations in the classical sense. Measurement generally affects the state, and because of that, expectation values must be understood statistically. So this is the correct foundation for what will come next, namely the derivation of the expectation value of position and the general expression for a quantum mechanical operator. Now let's begin with the expectation value of the position of a particle in state psi. Suppose a particle is described by the wave function psi. Since the absolute square of psi is the probability density for finding the particle at position x at time t, the natural question is, what is the average position we should associate it with this state? The answer is the expectation value of x, written as the angle bracket x, and it is defined as the integral of x multiplied by the probability density at x at time t over all space as shown in this expression. So this expression is in fact very natural if you think back to ordinary probability theory. It is a weighted average. Each possible position x is weighted by the corresponding probability density function there. So the expectation value is not just any average. It is the probability weighted average of all possible measurement outcomes. Now I want to emphasize a very important point shown on this slide. The expectation value of x does not mean that if you measure the position of one particle over and over again, the angle bracket x is the average of the results you will get. That interpretation would be incorrect in quantum mechanics. Why is it incorrect? Because once you perform the first measurement, the state is altered by the measurement process. So repeated measurements on one and the same particle do not keep sampling the original wave function. Instead, the expectation value of x is the average of measurements performed on a large number of particles, all prepared in the same quantum state psi. In other words, the measurements are performed on a large number of identically prepared independent systems. That's why the average of measurements is called an ensemble average, not the average of repeated measurements on one unchanged system. Now we can see the complete picture. If I prepare many identical systems, all described by the same wave function psi, and then I measure the position of a particle once on each system at the same instant, and finally average all those measurement results, then the average value I obtain is the ensemble average, denoted by the angle bracket, x. That is the physical meaning of the expectation value in quantum mechanics. So the expectation value of x should be interpreted statistically. It is the value of x we would obtain if we measured the positions of a great many particles described by the same wave function at some instant, and then averaged the results. So the key message of this page is the following. The expression shown here is the probability weighted average position of a particle in the state psi, understood as an average over many identically prepared systems, not repeated measurements on the same individual particle. Up to this point, we have written the expectation value of position as shown here, which is the integral of x multiplied by the probability density at point x and time t, carried over all space. Notice that the expression above can be rewritten as shown here, where the integrand has been rewritten as the complex conjugate of psi multiplied by x and by psi itself. We may then define the position operator in one dimension as x hat equals x. This means that when the position operator acts on a wave function psi, the result is simply x times the wave function psi itself. So with this notation, the expectation value of position can be now written as shown, where we just replace x here with x hat right here in this expression. And in bracket notation, this becomes the expression as shown, which is the standard operator form of an expectation value. So the position operator gives us our first clear example of how a classical dynamical variable becomes a quantum mechanical operator. In classical mechanics, position is simply the coordinate x. In quantum mechanics, the corresponding observable is represented by the operator x hat, which acts on the wave function by multiplication. So this slide is important because it begins the transition from probability density language to full operator language. Later we will see that other observables such as momentum and kinetic energy are represented by different operators, often involving derivatives rather than simple multiplication.